Hello, my name is Marcel Borowski and I am presenting the paper Varv, Reprogrammable Interactive Software as a Declarative Data Structure. This was a joint effort between me and my co-authors Klokmose, Rolf Bagge, Janus Kristensen, Arvind Satyanarayan and Clemens Klokmose. Today's software usually comes in the form of applications. Applications are constructed as packaged and turnkey products. This, as a result, gives end users only little room to modify their own applications in order to match them to their own needs. Even for trained programmers, it is often difficult to modify their tools. For example, in Google Tasks, which is part of Gmail, I can create tasks related to my emails. A task consists of a title, a description, and a due date. However, I cannot assign the task to someone else or add labels to tasks like I can do to my emails. Even adding such simple features in today's software model is either impossible or would require significant effort. As a response, we present Varv, a declarative language for reprogrammable interactive software that decouples specification from execution and is inherently extensible by the end user. Changes to code are immediately applied and enable a live programming experience and collaboration. The design of the Varv language is motivated by three design goals. First, we wanted to provide a structured and declarative representation. Declarative programming allows users to focus on the definition of interactive behavior, the what, while the system takes care of the implementation, the how. Varv achieves this goal by using declarative constructs written in JSON to define the interactive behavior of an application. Second, we wanted to make software accretively extensible. This means that interactive behavior can be modified through incremental addition without having to change the original code of an application. In Varv, any application can be extended by adding a new definition file, which can be used to add new or override existing interactive behavior. And third, we wanted to decouple application logic from interaction modalities. Existing methods of specifying interactive behavior often rely on callbacks to tightly couple an input event, such as a click or a key press, with an action. Retargeting an application therefore often requires significant manual effort. Varv instead decouples these two pieces. The Varv language is expressed in JSON. Concepts are the core building blocks of Varv. They define individual named units of interactive behavior, for instance, a to-do list or a to-do item. A concept contains schema and actions. The schema of a concept defines the shape and type of data associated with a concept. It does this in the form of properties. Properties can be either of a primitive data type, such as a string or a number, or they can be a reference to another concept. For example, the to-dos property in the to-do list concept is an array of to-do concept instances. Actions in the next step provide an abstraction for state transformations. Actions are named and consist of a when block and a then block. The when block defines an array of triggers that cause the then block to be executed whenever one of the triggers emits an event. Triggers can be either reactive, like in the update completed count action, or received from a view, like the click in the toggle completed action. The then block of an action can also refer to other actions, making it possible to nest actions inside each other or to create recursive actions. Lastly, being extensible is an essential part of the language design. Varv allows two ways of extensions. The first method is the merging and overwriting of JSON keys with another definition file. This makes it possible to add or override behavior without having to modify the existing code. This works similar to how CSS rules can be overwritten. For instance, we can create a second concept definition file in which we move the when block of the toggle completed action. The Varv event engine then merges the two files and combines the then block of the first definition with the when block of the second definition. The other way of extending concepts is through the use of one of the four extension mechanisms: inject, join, omit, or pick. In this example, we used the join extension to merge the two concepts to-do and assignable to create a new assignable to-do concept. Our main implementation of Varv builds on top of the WebStraits and CodeStraits platforms. It runs purely on the client side of a web browser and is implemented in JavaScript. WebStraits is a platform for creating reprogrammable and collaborative software on the web. WebStraits synchronizes and persists the DOM of a website with a server. This makes it possible to store concept definitions in the DOM and in doing so, making them collaboratively editable. Besides our main implementation, we also created 2 proof-of-concept implementations of Varv using Electron and Observable, which are independent of web states. This short example demonstrates how an existing collaborative to-do list application created with Varv can be extended in only 2 steps. In this example, we want to add an assigning feature to to-dos similar to the one we missed in the Google Tasks example earlier. First, we have to create a new property in the to-do concept. To do this, we first have to open WebStrait's built-in authoring environment Cauldron. In Cauldron, we create a new concept definition and add the code to add the property assignee to the to-do concept. In the inspector of Cauldron, we can then check whether the property is part of the to-do concept now. Second, we need to display the property in the view. We do this by creating a new template file and copy the existing to-do template over. We add an input field and set its value to the assignee property, and we are done. While we edit the template, changes are immediately updated in the application. To explore the expressiveness of Varv, we also created other applications like a board game toolkit. The toolkit consisted of a set of actions like piece picked or turn switched. These actions allowed us to create both the checkers and Othello board games using the same underlying set of actions, and even combine the rules of both games with little effort. Besides this, we also created an UI designer app similar to Figma. It lets users create screens of interface designs with elements like buttons on it. Elements can be moved and resized with the mouse cursor and can link to other screens. In the preview mode, interactions can then be tested. And lastly, we explored new ways of tooling that were enabled by the structured declarative representation, such as a view inspector that makes it possible to inspect concept instances and their interactive behavior in the user interface. In our paper, we evaluated the feasibility and explicitity of Varv through demonstration using case studies and examples. Future work is needed to evaluate Varv's usability in a user study. Through the examples we built with Varv, we have also demonstrated that the ceiling for what can be achieved with Varv is high. However, we do not clearly know its bounds in terms of expressivity or performance. Future work on this could involve comparative benchmark studies or the implementation of more challenging graphical user interfaces. Lastly, by representing interactive software as a data structure, Varv makes it possible to programmatically reason about the composition of applications. This information could be used to analyze interactive behavior in order to programmatically autocomplete or recommend interaction designs. With Varv, we have demonstrated that the declarative approach to specifying interactive applications as a data structure is not only possible, but also provides a range of powerful capabilities. We hope that Varv inspires future research to enable also non-programmers to develop interactive software.